Subsets. For two sets A and B, we say that A is a subset of B if every element of A is an element of B. We use this symbol that looks like a sideways U with a line under it for the subset relation. So this is read A is a subset of B. So A is a subset of B if for every x, x in A implies x in B. Symbolically, we can write the following. This upside down A here is called a universal quantifier. It's pronounced for all. So this whole statement can be read for all x, if x is an element of A, then x is an element of B. The first part here, for all x, is the upside down A followed by the variable x. The x epsilon A is read x is an element of A. And similarly, x epsilon B is read x is an element of B. The right arrow, remember, is a logical connective symbol, and it's used to express if-then. Okay, so again, we have for all x, x in A implies x in B. Or for all x, if x is an element of the set A, then x is an element of the set B. That's what it means for A to be a subset of B. Let's look at a picture of this situation. Let's focus on the circles in this picture for a moment. We have a circle representing the set A and a circle representing the set B, and notice that the circle representing A is fully included in the circle representing B. This type of picture is known as a Venn diagram. We'll be seeing several of these as we explore sets and subsets. The U here is called the universal set. So we usually have a box with our individual sets that we're interested in that box, and the entire box is representing the whole universe. So the universal set is just some set which includes everything that's in all the sets that we're interested. It may or may not have additional elements as well. For example, we could consider the universal set U to be the set of species of animals, and we could let A be the set of species of cats and B be the set of species of mammals. Note that every cat is a mammal and every mammal is an animal. So this Venn diagram represents this situation nicely. We have A, a subset of B, a subset of U. To show that a set A is a subset of a set B, we need to show that this expression for all x, x in A implies x in B is true. If the set A happens to be finite and the elements are listed, we can just check that each element of A is also an element of B. Let's look at an example of this. So let's let A be the set consisting of the elements A and B, and let's let B be the set consisting of elements A, B, and C. So we could just check one at a time that each element of capital A is an element of capital B. See, little a is in there, little b is in there. So we have that A is a subset of the set B. Now, if instead of listing the finitely many elements of the set A, suppose that the set A is described by a property. Say A is equal to the set of X such that the property P of X is true, we might need to craft an argument more carefully in this case. We'll usually do this by taking an arbitrary but specific element little a from the set capital A, and then arguing that this element little a is in the set B. Okay, so what do we mean by an arbitrary but specific element of the set A? Aren't those two expressions opposite of each other? Well, by arbitrary, we mean that we don't know which element we are choosing. It's just some element little a that satisfies the property P. So we're just assuming that P of A is true. However, once we choose this element little a, we use the same a for the rest of the argument. That's what we mean by it being specific. Let's use these ideas to prove a theorem about subsets. We'll start with a very simple theorem. Every set A is a subset of itself. Before writing the proof, let's think about our strategy. We want to prove that A is a subset of A. In other words, we want to show for all x, if x is in A, then x is in A. So we'll take an arbitrary but specific little a in A and then argue that little a is in A. But that's pretty obvious, isn't it? In this case, the property describing the set is precisely the conclusion we're looking for. So let's try and write out the proof now. Let A be a set and let little a be in capital A. Then little a is in capital A, right? We just said it, so it's true. So A and A implies A and A is true. Since little a was arbitrary, the statement for all x, x in A implies x in A is true. Therefore, A, a subset of A, is true. Okay, just a few comments about this. The first sentence, let A be a set and let little a be in big A, is called the opening statement. In general, the opening statement states what is given in the problem and fixes any arbitrary but specific objects that we will need. So in this example, the opening statement states what is given. That's we're taking an arbitrary set A, and we're fixing the arbitrary but specific object little a inside of the set big A. The last sentence here, therefore A is a subset of A is true, is the closing statement. In general, the closing statement states the final result. Everything between the opening and closing statement is called the argument. This last little symbol, this square at the end, is just a symbol we place at the end of a proof to indicate that the proof is complete. Some notes here. Consider the logical statement P implies P. This statement is always true, right? Because true implies true is equivalent to true, and false implies false is equivalent to true. P implies P is an example of a tautology. A tautology is a statement that is true for every possible truth assignment of the propositional variables. If we let P represent the sentence A and A, we see that A and A implies A and A is always true. It's a tautology. We can use these ideas to write a slightly different proof of this theorem. Let A be a set and let little a be an A. Since P implies P is a tautology, we have that A and A implies A and A is true. Since little a was arbitrary, the statement for all x, x in A implies x in A is true. Therefore, A, a subset of A, is true. End of argument. Let's look at another theorem. the empty set is a subset of every set. Before we write the proof, let's analyze the situation. This time, we want to prove that the empty set is a subset of A. In other words, we want to show for all x, x in the empty set implies x is in A. Since the statement x in the empty set is always false, because the empty set has no elements, the statement x in the empty set implies x in A is always true. In general, if P is a false statement, then we say that P implies Q is vacuously true. Let's go ahead and write out the proof now. Let A be a set. The statement x in the empty set implies x in A is vacuously true for any x. And so, the statement for all x, x in the empty set implies x in A is true. Therefore, the empty set is a subset of A. End of argument. The first sentence, let A be a set, is our opening statement. And the last sentence, therefore, the empty set is a subset of A, is our closing statement. Okay, let's look at an example here. Let's let C be the set consisting of elements A, B, and C, D be the set consisting of elements A and C, E be the set consisting of elements B and C, F the set consisting of B and D, and G the empty set. Let's look at the various subset relationships between these sets. Well, D is a subset of C. Notice that A and C are both in the set capital C. E is a subset of C. The elements B and C are both in the set capital C. The empty set is a subset of every set. That was the last theorem that we just proved. So here the empty set is being labeled by the set G. So we have that G is a subset of all these sets that are listed, C, D, E, F, and G. Also, every set is a subset of itself. So C is a subset of itself, D is a subset of itself, E is a subset of itself, and F is a subset of itself. Here's a nice Venn diagram of this situation. You might want to take a look at this and compare it to the sets we have written down here. For example, the set D has the two elements A and C, and so it's a subset of C. And notice how in the Venn diagram, the set D sits completely inside of the set C. Similarly, E is a subset of C. And let's also just throw in the elements into this Venn diagram. So we could see these relationships nicely. We threw in a few more elements, E, F, and G, into the universal set. Those are somewhat arbitrary. We could throw whatever we want in there or nothing in there. So in this case, we decided to let our universal set consist of the elements A, B, C, D, E, F, and G. Note that our universal set must contain A, B, C, and D because those are elements of the sets that we're talking about. The E, F, and G we threw in just to have a few more elements there. We could have put in more elements or less elements. Okay, let's look at another example. Let A be the set AB and B be the set ABC. Let's start by looking at the set A. The set A has two elements and it has four subsets. Let's look at the subsets of A. Well, there's the empty set. Remember, the empty set is a subset of every set. And then we have the set consisting just of A. That's a subset of set capital A. And the set consisting just of B. And then remember that every set is a subset of itself. So the set AB is also a subset of itself. Notice that the size, or the cardinality, of the set A is 2, and the cardinality of the collection of subsets of A is 4. This expression P of A is pronounced the power set of A, and it consists of all subsets of A. In this case, the power set of A is the set containing the four subsets of A, namely the empty set, the set containing A, the set containing B, and the set containing both A and B. And now let's look at the set B, which has 3 elements and 8 subsets. Okay, let's write down the subsets of B. Well, again, there's the empty set, because the empty set is a subset of every set. There's the set consisting of just A, the set consisting of just B, and the set consisting of just C. And then we have the set consisting of A and B, the set consisting of A and C, and the set consisting of B and C. And finally, we have the whole set B consisting of all 3 elements A, B, and C. Notice that there are 8 subsets in total. The cardinality of B is 3, and the cardinality of the power set of B is 8. Okay, and here's what the power set of B looks like. It's the set consisting of these 8 subsets. Let's draw some diagrams of the subset relation between the various subsets of each of A and B, starting with A. This is a nice little tree diagram of the set A. Notice that at the top we have the subset of cardinality 2, which is the set itself. And underneath that we wrote the subsets of cardinality 1, the set containing A and the set containing B. And at the bottom we have the only subset of cardinality 0, the empty set. The lines connecting these sets are there to illustrate the subset relation. The empty set is a subset of A, and the empty set is a subset of B, so we have a line for each of those. And each of the sets containing A and the set containing B is a subset of the set containing A and B, so we have lines showing those relationships as well. There are also a couple of hidden relationships here, right? Because the empty set is a subset of the set AB, and we can see that by tracing either the lines on the left from empty to A to AB, or the lines on the right from empty to B to AB. And here's a tree diagram for the set B. We have the set with 3 elements at top, the subset consisting of 2 elements underneath that, and then the subsets consisting of 1 element, followed by the empty set at the bottom, which is the only subset with 0 elements. You can see all those nice lines illustrating the various subset relations that the set B satisfies. So how many subsets does a set of cardinality n have? Let's make a little chart of this situation to try to make an educated guess here. We'll label the columns with the cardinality of a set A with that cardinality, then the power set of that set A, followed by the cardinality of the power set of A. So we're going to run through various values of n. So we'll look at specifically n equals 0, 1, 2, and 3. So when n is 0, the set A doesn't have any elements. So I just put a little dash to indicate that. And the power set of A consists of just the empty set. The only subset of the empty set is the empty set. So the cardinality of the power set of A is 1. There's one subset of A here, just the empty set. Now when n is 1, our set has 1 element. Let's call it little a. So the power set of A consists of the empty set and the set consisting just of little a. There are 2 subsets in this case. For a 2-element set, let's name the elements A and B. Then the power set of A has the 4 subsets, empty, set containing A, set containing B, and the set containing A and B. Notice that the cardinality of the power set of A here is 4. And let's do one more example, a set with 3 elements. Let's name those elements A, B, and C. In this case, the power set of A has 8 elements, right? Empty, set A, set B, set AB, set C, set AC, set BC, and set ABC. Notice the pattern here. 1 is equal to 2 to the 0, 2 is equal to 2 to the 1, 4 is equal to 2 to the 2, and 8 is equal to 2 to the 3. So I think we could make a pretty educated guess as to what the size of the power set would be if the size of the set A is n. Okay, well, if the cardinality of A is n, then it seems reasonable that the cardinality of the power set of A will most likely be 2 to the n. Let's go through another theorem. Let A, B, and C be sets such that A is a subset of B and B is a subset of C. Then A is a subset of C. Let's go ahead and try and write out the proof here. Our opening statement is the following. Suppose that A, B, and C are sets with A a subset of B and B a subset of C, and let little a be in A. Notice how I stated what we're given, and I fixed an arbitrary element of set capital A. Okay. Since A is a subset of B and little a is in A, it follows that little a is in B. Here I just used the definition of what it means for capital A to be a subset of capital B. And now I'll do the same thing with B and C. Since B is a subset of C and little a is in B, it follows that little a is in C. Since little a was an arbitrary element of capital A, we have shown that every element of A is an element of C. That is, for all x, x in A implies x in C is true. Therefore, A is a subset of C. And that's the end of our argument. Okay, this last sentence is our closing statement. Here's a nice Venn diagram of this situation. Notice we have sets A, B, and C inside of our universal set U, and A is inside of B, and B is inside of C. It's pretty easy to see from this picture that the set A must also lie inside the set C. So this picture gives us strong evidence that if A is a subset of B and B is a subset of C, then A is a subset of C. Notice, however, that only the proof that we just presented right above this picture tells us for certain that this statement is actually true. In this case, we say that the relation subset is transitive. Let's look at an example of a relation that's not transitive. So in this example, we'll show that the relation epsilon is not transitive. Well, here's an example to show this. Let's let A be the empty set, B be the set containing the empty set, and C be the set containing the empty set. Then A is in B, right? Because B contains the empty set as an element. And B is in C because C contains the set containing the empty set as an element. But A is not in C. The empty set is not an element of C.